Hello, welcome to another screencast where this time we'll be discussing muscle physiology 1A, part of the excitation contraction coupling mechanism. So in order to really get the most out of this, you should review first the action potential generation and propagation back from the nervous system and understand the structure and function of the neurochemical synapse, because this is really what the meat of this is here about the synapse and what's going on there, but just at a specialized synapse. Also, understanding and knowing the microanatomy of the skeletal muscle and the skeletal muscle fiber, that is the cell, is extremely important. We're going to focus here on first describing and explaining here the structure and function of what we mean by a motor unit, and then getting into the activities of the neuromuscular junction to include the roles of acetylcholine, the sarcolemma, the Ttubules, the sarcoplasmic reticulum, and then a little bit about the importance of calcium ion. Okay. So let's get started here. The skeletal muscle fibers are under nervous control. They are under voluntary nervous control. And so here we see a section of the spinal cord, and we see motor neurons right here. These are multipolar neurons. So here's your cell body and dendrites here. And then here are your long axons leaving the spinal cord via the ventral root here, and then forming a nerve. And again, a nerve is a collection of axons in the peripheral nervous system. And what we're showing you here are two motor units. Right? And so the motor unit is comprised of the axon and any and all muscle fibers that it innervates. Right? So again, the word I'm saying there is innervate, and that is a term from the nervous system where the neuron, so let's just take motor unit number 1 right here and follow it. So here's the axon. You see this axon is going to branch to form a neuromuscular junction here with this skeletal muscle fiber, and then it's going to branch and form a neuromuscular junction with this muscle fiber right there. So let's go ahead and label these a second. So these are A, B, C, D, and E. So motor unit number 1 is innervating muscle fibers B and E. Motor unit 2 is innervating muscle fibers A, C, and D. Right? So motor unit 1 is innervating 2 muscle fibers, and motor unit 2 is innervating 3 muscle fibers. Now, the nervous system is able to regulate which of these neurons the action potential is being sent down. And if we send the action potential down motor unit 1, pardon me, then you're just going to get muscle fibers B and E contracting. If you send it just down motor unit 2, then you'll get A, C, and D contracting. So motor unit 1 would be for if you needed less force. Motor unit 2 would be if you needed a little bit more force. And then if you used motor unit 1 and 2 together, you'd be getting maximum force out of that fascicle right there. So the nervous system is hooked up to be able to regulate the amount of contraction, or the number of fibers contracting. So in general, the more fibers you signal to contract, the more force you're going to be able to generate, the more tension you'll be able to generate, the heavier the load you'll be able to move. Right? So here we see a light micrograph of these axons branching, and you can see the axon terminals at the neuromuscular junctions. Here we have these slides in the classroom, so I would encourage you to take a look at them. And we've seen this from another screencast previously, but again, you can see the motor end plates very clearly here. This is part of the axon branch, and then this again is the skeletal muscle fiber there. So we're going to go look and see here what's going on with these end plates. Right? Again, more of the same, but let's look at a cartoon version here of what's happening. So in the chemical synapse from the nervous system, we had this axon, and it was joined up to the dendrite of another neuron. So we had a neuron synapse here. The same concept is going to be happening here, except for we're not going to have a neuron as the second cell here. We're going to have a skeletal muscle fiber as the second cell now. So you're going to say that this right here is the cytoplasm and the cell membrane of the muscle cell. So this would be the sarcolemma, the muscle fiber membrane. And then this would be the cytoplasm, or the sarcoplasm rather, I should say. So this is the sarcoplasm of that muscle fiber. So the action potential is going to travel down the neuron and is going to reach that terminal axon, and it's going to cause the release of neurotransmitter. So here we see the vesicles fusing and dumping neurotransmitter into the synaptic cleft, or the synaptic gap. And that neurotransmitter is going to diffuse across, bind to a sodium channel, which is closed. When it binds, it opens. When the neurotransmitter binds to the sodium channel receptor, the sodium channel opens. Sodium will then diffuse in, thus depolarizing the cell. When the neurotransmitter is broken down and released, that sodium channel is going to close, as we see here in this diagram, and you're not going to get any depolarization happening there. So again, there are animations that set this in motion much better than the static diagrams, but this is what's happening. So I'd recommend running the PowerPoint and taking a look at those animations. Skeletal muscle cell, or the skeletal muscle itself, going down to the fiber level. I want to point out here that the T-tubules are going to come into play here in just a second. So the action potential is going to be generated on that sarcolemma, and it's going to travel this way and then travel down those T-tubules. In class, we've discussed what the T-tubules look like, but I think the animations do a much better job of that. There's going to be an interaction there between the T-tubules and the sarcoplasmic reticulum, those terminal cisternae there. You're going to mention this word triad, and the triad is just that, is just the terminal cisterna of one endoplasmic reticulum segment, the terminal cisterna of a second sarcoplasmic reticulum network, and then the T-tubule itself. So this is why you get a triad. You get three things all together. There are two sarcoplasmic reticula and one T-tubule structure there. So when we zoom in on that, this is what we're going to see right here. So the action potential travels down the neuron, travels down the axon, reaches the axon terminal. That is going to cause the synaptic vesicles that are loaded with neurotransmitter. And at the neuromuscular junction for skeletal muscles, the most popular one, is neurotransmitter that is acetylcholine. Acetylcholine, also abbreviated big A, big C, little h. So this is acetylcholine. That is the name of the neurotransmitter. Acetylcholine diffuses across the gap, will bind with receptors that then open sodium channels, and you then get an action potential generated on the sarcolemma. That action potential will be propagated down the sarcolemma in much the same fashion that it gets propagated down an axon. The action potential then travels down the T-tubules that dive deep into the cytoplasm area of the cell. I do want to point out that this is still the sarcolemma right here. So this is outside the cell. This is inside the cell. That action potential will trigger now calcium channels here in these terminal cisternae. So there's a calcium channel there that's voltage sensitive, and we've seen voltage sensitive channels before in the action potential, and there we were dealing with voltage sensitive sodium and potassium channels, but here we're dealing with a voltage sensitive calcium channel. So the voltage sensitive calcium channels will open. That will then release calcium ion out of the sarcoplasmic reticulum into the cytoplasm. And that calcium ion will then bind with troponin, moving tropomyosin off, as we see here, and initiating the cross-bridge cycling here, which we'll deal with in another screencast. Okay. Want to point out that if acetylcholine is present, you get all this happening. If acetylcholine is not present, then you don't get this happening. So a way to regulate this would be a way to vary the acetylcholine that's in the cleft right there. If the acetylcholine stays put, then you're going to get constant muscle contraction. If you don't have enough acetylcholine released, then you're not going to get muscle contraction. Similarly with calcium, if the calcium gets released, then you have muscle contraction. If you don't get calcium release, then you are not going to have the muscle contracting. So little intermediate players there, the acetylcholine and the calcium ion. These are potential ways to regulate the contraction of the skeletal muscle. Again, would recommend taking a look at that animation as well to put this all in motion for you. Okay? So hopefully now you have a little bit better grasp on, first of all, what the motor units are and what their basic structure and function is, as well as then the activities at the neuromuscular junction. So we talked a little bit about acetylcholine and its role, the role of the sarcolemma, the role of the T-tubules, and the sarcoplasmic reticulum with calcium ion there as well. Okay? Thanks for listening. Bring your questions, concerns, clarifications to class. See you then.